Hello and welcome to section 3, defining causality, structural causal models. This is what we covered in the previous section. We covered intervention, the do operator, and in this section I want to dive deeper into the definition of causality. So, does intervention or the do operator really define causality? Or perhaps they better serve as just tools that reveal causality. And I want to explain the point via this example. Consider the independent binary random variables x and z that follow the Bernoulli distribution with mean 1 over 2. And I define y as an XOR function of x and z. Okay? Then the following holds although x is causing y. P of y condition on do of x equal to 0. So if I put x equal to 0 here, is equal to P of y condition on do of x equal to 1. Regardless of whether I put x 0 or 1, because this is an XOR, the probability of y then will be 0.5 for y equal to 1 or y equal to 0, because it all depends on the value of z, and z is following a Bernoulli distribution with mean 0.5. So this is, both of them are equal, and they are equal P of y. It's like y is independent of the intervention on x. Now, this is despite the fact that we just defined how y is a cause, how x is causing y. Okay, so we see that the causality test that we defined in the previous section fails here. One may argue that, well, the problem is solved if we additionally include the z variable. It's all because we're not observing z. This is true. So if I put z equal to 0, and then I intervene on x, then indeed the value of y will be different. Okay, so in one case, it will be 1. In another case, it could be 0. Yes, but first of all, we often are not aware of such a second cause, the existence of such a second cause, okay? And secondly, intuitively, when we talk about causality, do we really immediately think of such a complicated test? Now, you can imagine more variables involved here. Do we think of a distribution of y conditioned on some observations and some intervened variables? Probably not. Then, how do we think about causality? Well, one possibility is the functional form that we defined above. Okay, let's see that in an example. Consider the following example: COVID, cough, and drug. If we interpret the links as causal relationships, then we have that COVID is causing cough, and cough is causing whether the individual will take the drug or not. Now, we know that there are more influencing factors that along with COVID lead to cough. However, I mean, it's not just COVID, there could be several other reasons, but we are not modeling them explicitly here. We just include them as a single exogenous or latent variables U of O for cough, which all capture a long vulnerability. Okay, and similarly for the other ones, COVID and drug. Taking drug does not just depend on cough, and COVID depends on. It's not that nothing can cause COVID. There are some things causing it. So we denote all of these external variables in this form: U of C, U of O, U of R, where U of C stands for weakness in the immunity system. Long vulnerability for U of O, and willingness to take medicine, U of R. A structural causal model, SCM, is exactly this. This is, well, the representation. But in SCM, we include these variables as exogenous variables along with the endogenous variables, COVID, cough, and drug, and we will determine their relationships via deterministic function. So here we will assume that C is just equal to U of C, but you see that it's a function of this exogenous variable u of c. O is a function of the exogenous variable u of O and its parent COVID. And it's deterministically determined here. This is basically an XOR function. For drug, same story. It's a function of its exogenous parent and its endogenous parent. Okay, so you could have different functions as well. Okay, so that was how we defined causality. Just note that in a sense, everything is deterministic here. There's no probabilities, there's no stochasticity except for these exogenous variables. But if I know them, and if I know the value of my parents, then I know exactly what this value for this node will be for any of the nodes. Okay, and perhaps this is a more intuitive way of thinking about causality. Now, to make it formal, we define a structural, or also known as functional, causal model, SCM, as a tuple VU PUF, where V is the set of endogenous random variables, U is the set of exogenous latent or noise random variables. You see, it's a collection of U of X, so corresponding to each X in V, we have one UX. And of course, we determine the distribution of U. So P of U is the joint distribution over U, which we assume that they are mutually independent. P of U will be just the multiplication of each of these exogenous variables. Most importantly, the F component, which is the set of functions fx that determine or simulate how values are assigned to each variable x in V based on a subset of endogenous variables, which are known as the parents of x, and based on the parent exogenous variable u of x that we define here. Okay, so x is a function of its parents, some variables known as its parents, and its corresponding exogenous or noise or latent variable u of x. Now you see this, we're putting this double dot and equality sign here. This means that, well, it is assigned to x. It's not that like x can be assigned to this f of x. It's a one-way assignment. Okay, it's this is how we denote causality. Sometimes an arrow is used to denote this this term. So that this definition is somewhat capable of capturing the idea that if we know all of the causes of a variable, then we can determine its value. We discussed this in the previous slide. Now here we impose a minimality assumption. The function fx does depend on all of its parents. None are redundant. So for example, here, if I had 0 and instead 1 here, then O would basically depend only on the value of u of O. It would be 1 when u of O is 1, and it would be 0 when u of O is 0. It wouldn't depend on C. So we're excluding this possibility. We're saying that once we write this down, it means that fx really depends on all of them. And finally, the condition 3 means that ux's are jointly independent. Great. Now, an SCM entails a causal graph or network over nodes V where the parents of every node are linked to it. Okay. Here we're assuming that the graph is acyclic, so it will be a DAG, and the parents of a variable are known as its direct causes, and the ancestors are known as its indirect causes. Here is an example. The SCM and causal network for the XOR example are here. So we have the SCM representation. X and Z were causing Y, and X was following a Bernoulli distribution, so I will have X equal to its exogenous parent U of X, where Ux is following a Bernoulli distribution, and same with Z. And for Y, I have that it's a XOR function of X and Z. U of Y is 0, so I'm not writing it down here. And well, this will be my causal model. Everything is clear, like how Y exactly depends on X and Z. Note that once I know the value of X and the value of Z, the value of y here is exactly determined. Okay. Now the causal network that we define here is basically the same. So I will, for each variable like y here, I will link its parents x and z to y. It's also represented here, just that I wouldn't include these exogenous variables. And this will be my causal network. The ones here that are directly linked to it are its direct causes, and those here I don't have any, but if I had something here, then that would be an indirect cause. It makes defining this direct causality, indirect causality so simple. With the do operation, you can test that it wouldn't be this straightforward. Okay, now I have this. What else does an SCM entail? Well, note that although the relationships are defined deterministically, an SCM entails a unique observational distribution, which is basically the joint probability distribution P of V. So where does this come from? Well, if you have a look here, I have my variables, but I also have some noises here that have some distribution, and from there I can define a joint probability distribution on all of the values. Okay, great. We will get back to this example. Now, what can I say about this P of V? Well, indeed, because x depends only on its parents and its exogenous parent, and also the fact that the exogenous parents are jointly independent, I can conclude that each variable x is independent of its non-descendants conditioned on its parents. Okay, so x only depends on its parents, or for example here, y only depends on its parents x and z. If there were other nodes here, we wouldn't care. The definition here says that once I know the parents and perhaps the exogenous parent, then I know the value of y. I don't care about the other nodes. Well, okay, what does this imply? Back to chapter 1. Well, this means that the causal network G that we just defined is an IMAP for P. So P factorizes according to the corresponding causal graph. So I can write down this Bayesian network factorization where P is obtained from these parents, the definition of the functional definitions for each node. Okay, so how can I get them? I can get them from here. Again, we will see an example soon. So from here, I can conclude that any probabilistic query, P of y condition on z, can be answered using this formula, right? So again, these are material back from chapter 1. I can write down P of y condition on z as P of the joint distribution, P of y and z divided by P of z. By definition, P of y and z will be marginalizing out from V everything except y and z, and we can do this a similar thing for the denominator, and P of V is just factorized according to this formula. Okay, so I can answer any inquiry like this. Great, let's see the example. In the XOR example, if I want to calculate the joint distribution of P of x, z, and y, well, according to the factorization, or because this graph is an IMAP, I can write it down as P of x, times P of z times P of y condition on its parents. Now note that these are the small letters, meaning that they are the values. But what can I say about P of x? It's basically equal to P of u of x. And the same with z. What about y? Well, y here, P of y condition on x and z, it will be 1 if y is exactly an XOR of the two. It will be 0 if anything else is happening, if it's not equal to the XOR of these two. So for example, if I have x1, z1, and then I put 1 here also for y, then this should be 0. And this is how I'm defining it. So this is the joint distribution. You see that from an SCM, I am able to get the joint distribution of my variables. Okay. So the causal network serves as the structure of a Bayesian network because it's an IMAP. And we therefore get this remark, answering probabilistic queries. If augmented with the CPDs, P of X condition on parents of X, and we explain how we can get them, the causal network turns into a Bayesian network that answers probabilistic queries, P of Y condition on Z for all Y and Z. Okay, great. What about the do operation? The interventions and the story with that. How to perform the do operation in SCM? For example, how to perform do of y equal to 1 in the following extended XOR. Okay, so I additionally have the node W here. I'm putting uy here as well. But W, this is the formula. It's 2 times y plus u of W. So I want to make intervene on y. That means that I want to set the value of y to 1. Well, that simply means that in this equation, I just need to set y equal to 1. And that means that y does not depend on its parents anymore. Nothing else will change. So here I will have y equal to 1, and I'm removing the incoming links to y. This will be my new SCM. And I can, the same story, I have again a causal graph, I can answer queries and so on. Right? Now, also note that intervention can also be imperfect or parametric. An imperfect intervention is also known as a mechanism change, where pre-intervention causes still will have some effect. They're not completely removed. And we can cover this in an SCM. So for example, in the fire smoke example, an imperfect intervention on fire would be to lower the temperature in order to reduce the probability of fire. And we do this rather than completely preventing it, as we saw in the previous chapter. Okay, this will be an imperfect intervention. So instead of setting the value of y to a fixed value, say 1, we change its assignment f and noise uy to some other assignment f prime and noise u prime of y. So, well, in some cases, f prime may equal to f or u prime may equal to u, but the point is that you see here, parents of y still appear. At least some of them will remain here. Just the mechanism of how y is generated from its parents is changed. This is the mechanism. And this change of mechanism may appear as a parametric form. In the XOR example, for example, if one way of doing an imperfect intervention is to set the value of y not anymore to XOR, meaning that x, but to something like x minus z, plus u prime of y, where now the distribution of this has changed. Previously it was 0. Here, for example, it could be a Bernoulli distribution. So we will have the links, but the formulation here is changing. Okay, this is how we capture imperfect intervention in structural causal models. So what does this entail? Well, after doing this imperfect intervention, what happens is that the joint probability distribution, or more specifically, the CPD of y will change. It is no longer as when it was equal to, for example, x or z. It will get a new distribution, we can calculate it, and this is how we can write it down. Okay, like a P star. Great. Now, in either case, whether I have a perfect or an imperfect intervention, the intervened SCM again entails a probability distribution over all the variables. Why? Because at the end of the day, after intervention, I will still have an SCM. So similar to the original SCM, it will still entail a probability distribution. Just that this time, for example, in the perfect case, y will no longer depend on its parents. Okay? Now, this new SCM, it still induces a causal network, and none of our previous independencies are lost. We may just have some new ones. For example, here, if it in the perfect intervention, we still have all of the independencies, like W does not depend on X and Z condition on Y. That still holds. The only thing is that we may have some new ones, like Y now no longer depends on its parents. Okay, so that means that again, we can factorize the network according to the causal graph. In the XOR example, we can find this distribution, the intervention distribution, in this form. So P of X, Z, and do of Y and W. I can factorize the distribution according to the graph, or even to the previous graph where I had the node. So it will be P of X, P of Z, P of W condition on Y, and P of Y condition on X and Z, where here it's just set to 1. So P of Y will be equal to 1, unless we're asking where a query where Y is different from its do value. But here it's just 1, and I can calculate each of these. So this will be U of X, U of Z. W condition on Y, well, this is the same as U of W equal to W minus 2, because here you see that this will be 2 and UW will be W minus 2. So I will have the joint distribution. I can calculate it explicitly once I have the values of X, Z, and W. What did happen right here was that I transformed an intervention distribution or an intervention query into a non-intervention or observational query. Okay, and this is a very important point. So you see in the last one I don't have any do. In the first one I do have. And this is the point that a perfect intervention query, P of Y condition do of Z and X, can be answered as P of Y condition on Z and X in the previous Bayesian network, with the main difference that all incoming edges in the intervened node Z are removed, and the intervened variables are fixed to the intervention values Z equal to Z. Okay, and this brings us to the important point, notion of mutilated network. Given a Bayesian network B, we obtain the mutilated network B of Z equal to Z, this is the notation, by removing the incoming links to the set of nodes Z and setting their values to Z, the small letter Z. And by setting their values, we mean that P of Z equal to Z prime is 1, or even if it's conditioned on its parents, is 1 if Z prime equals to Z and is 0 otherwise. Okay, so another remark, answering intervention queries. If augmented with the CPDs, the causal network turns into a Bayesian network B that answers intervention queries, P of Y condition on do of Z and X, as follows. So this intervention query will equal to the mutilated network, the probability of Y condition on Z and X in the mutilated network. In a sense, this is amazing because we're able to now answer experiments or interventions without literally doing them. We can now turn them into a probabilistic query and answer them in the ways that we already know. Okay, the last point here is that the essential property that enables us to answer intervention queries is the so-called modularity property. The conditional probability of a node is affected only if the intervention is on its parents. Otherwise, it's not affected. Consider variables V with intervention and observational distribution P. A DAG over V is modular with respect to P if for all Z as a subset of V, P of Y condition on its parents and do of Z is the same as when you ignore do of Z, P of Y condition on its parents, as long as the intervention is not on Y. Okay, so this means that only the point that you're intervening is affected, not the rest of the graph. So it's modular. So the entailed causal network from an SCM is modular with respect to the entailed probability distribution. We just captured the property formally here. Now, what does it imply? Well, the property may not hold if one of the observed causes of node Y is not included as its parents in the causal network. For example, if Z is indeed a cause of Y and I didn't include it there, then this equation will no longer hold, because I will intervene on Z and the distribution of Y will change, so I can no longer say that it equals the conditional probability. And this means that, roughly speaking, all causal relationships are included in the graph. It is not violated, though, that if there are extra non-causal links. Okay, we'll talk about this more in the future chapters, future sections. Just note that here, of course, I'm excluding the exceptions. For example, there may exist some variable Z as a cause of Y that, even though I intervene on it, this distribution will not change, similar to the XOR example. Okay. Now, to wrap up, we were concerned with how to define causality, and we introduced the SCMs. And in the next sections, I want to talk more about like how can we get from data to somewhere close to this question of causality, or SCM.